Module 2, Lecture A, Estimator Interface. By the end of this lecture, you will be able to explain the roles of estimators, predictors, transformers, and meta-estimators. Use fit, predict, transform, fit transform, and score appropriately. And inspect and update estimator parameters without confusing them with learned attributes. API roles. Estimator basics. In the Estimator API, an estimator defines how a model will learn before training begins. Its parameters set choices such as regularization strength or tree depth. But the estimator is only a plan until it is fitted to data. After fitting, it learns patterns from the dataset and becomes a trained tool for making decisions or predictions. An estimator is a general tool for data processing, not just prediction. It can support tasks such as classification, clustering, scaling, and dimensionality reduction through a shared pattern of configuration and training. Before training, it contains user set parameters. After training, it also contains attributes learned from the data. Keeping this distinction clear helps avoid mistakes, such as expecting learned results before the estimator has been fitted. Estimators provide a common way to build and compare machine learning tools across different tasks. They can train classifiers, predict healthcare risks, standardize data, or group customers without labels, all using a consistent workflow. This unified approach makes it easier to focus on what each estimator learns and how its trained state can be used effectively. Predictors and transformers. In machine learning, a predictor is an estimator that learns patterns from labeled data and uses them to make predictions on new examples. After training, it should generalize to unseen cases, which is central to supervised learning, where both inputs and target values are known. A transformer changes data into a more useful form for later analysis, rather than making predictions. It may standardize values, reshape data, or create features, such as turning raw sensor readings into daily averages. It learns the needed transformation rules from existing data, like scaling settings or category encodings, and then applies them consistently to new data. In machine learning, transformers prepare data, such as by filling missing values or scaling features, while predictors produce the final output. Keeping these roles separate makes workflows easier to understand, test, and apply consistently. Even when an estimator can do both, it is important to know whether it is transforming data or making predictions, because this supports reliable and maintainable pipelines. Meta-estimator wrappers. Meta-estimator wrappers do not create models on their own. They manage other estimators and add higher-level strategies around them. They can improve stability by training models on different data subsets or tune a model by trying different parameter settings. Even with these added processes, they keep a consistent interface, making them easy to use in larger machine learning workflows. Meta-estimators are wrappers that manage other estimators and coordinate how they work together. They can combine multiple models through ensemble methods or organize steps such as data cleaning and feature transformation through pipelines. By providing one unified interface, they make complex machine learning workflows easier to build, manage, and understand. Meta-estimators wrap other estimators to control how they are used, while leaving their core behavior unchanged. If the wrapped estimator predicts, the wrapper supports prediction. If it transforms data, the wrapper supports transformation. In multi-stage workflows, the available methods depend on the final component. Understanding this helps clarify how machine learning systems combine pre-processing, feature selection, and prediction under a consistent interface. Core estimator methods. Fitting the model. Fitting a model means an estimator learns from training data using its fit method. For classifiers, it learns patterns that separate categories. While for regression, it learns how features relate to outcomes. For transformers, fitting records data characteristics such as averages for later processing. In short, fitting turns an untrained estimator into a model prepared to work with a specific dataset. Use the fit method only on training data, never on data set aside for evaluation. Fitting lets the model or pre-processing step learn patterns, such as averages, so using evaluation data too early can contaminate the process and make results look better than they really are. Keeping training and evaluation data separate gives a more realistic measure of how the model will perform on new data. After an estimator is fitted, it stores what it learned from the data as learned attributes. These are different from the settings chosen before training, which guide how learning happens. The usual workflow is to configure the estimator, fit it to the data, and then use it to predict or transform. Without fitting, the model has not learned the data structure and cannot work effectively. Python code, fitting the model. This example shows how to fit a classifier. Fitting lets the model learn patterns from training data, and after that, it can make predictions and produce scores. We import key Scikit-Learn tools for a simple classification workflow. The Iris dataset loader, a function to split data into training and testing sets, and the k-nearest neighbors classifier. Together, these let us load a standard dataset, prepare it for evaluation, and build a basic classification model. We load the built-in Iris classification dataset from Scikit-Learn for demonstration. Its input features are the flower measurements, and its target values are the species labels we want to predict. Before supervised learning, check that the feature data and target labels have the same number of rows. Each data point must match exactly one label. If they do not match, an error is raised to prevent incorrect training or evaluation. The dataset is split into training and testing sets, so the model is evaluated on data it has not learned from. A quarter of the data is reserved for testing, and a fixed random seed makes the split reproducible. The split is also stratified by the target variable, keeping class proportions similar in both sets for a fairer performance evaluation. We create a k-nearest neighbors classifier that uses 3 nearby data points to make predictions. We also check the Scikit-Learn version for reproducibility and confirm that the model's neighbor setting is correctly set to 3 before training. The model is trained on the data by using its fit method, allowing it to learn patterns for future predictions. After training, checking the model's classes attribute shows the unique categories it learned, confirming that it captured the dataset's distinct classes. The trained model predicts the class of the first test sample. Then its overall accuracy is measured on the test set. The result shows the predicted Iris class name and the test accuracy rounded to 3 decimal places. This script shows a basic Scikit-Learn workflow using a k-nearest neighbors classifier on the Iris dataset. It loads the data, makes a stratified train test split, trains a model with 3 neighbors, and reports the learned classes. It then predicts the class of one test sample and evaluates overall test accuracy, illustrating the standard steps of training, prediction, and evaluation. Predict and score. After an estimator has been fitted, use the predict method to apply what the model learned to new data. Fitting is the learning step, while prediction generates outputs such as class labels or numeric estimates. Always fit the model before predicting, and make sure the new data has the same features and structure as the training data. The score method gives a quick summary of how well a fitted model performs on data with known outcomes, using the model's default measure, such as accuracy for classification or explained variation for regression. It is useful for comparing models during development, but it should not be treated as a complete evaluation. A high score can still be misleading in some settings, so it is best viewed as a model-specific summary rather than proof that the model is suitable for real-world use. When using prediction and scoring, keep training data separate from evaluation data. Scoring a model on the same data it learned from can make performance look better than it really is, because the model may be memorizing rather than generalizing. Train on one dataset and evaluate on different cases, such as new students or future time periods. Use prediction to produce decisions, and scoring to summarize how well those decisions perform. Python code, predict and score. After fitting a model, use its prediction and scoring methods to evaluate performance. For a fair assessment, test it on separate data. Then compare the predicted results with the score summary. We import key tools from Scikit-Learn to build a simple classification workflow. The Iris dataset loader provides a standard dataset. The train test split tool separates it into training and testing data. And the decision tree classifier creates an interpretable model for classification. We load Scikit-Learn's built-in Iris dataset to prepare for a classification task. The data includes flower measurements as features and species labels as targets, giving us the inputs and correct answers needed for later processing and model training. The code verifies that the feature data and target labels have the same number of entries, so each feature row has a matching label. If they do not align, it raises an error. This check helps prevent mismatched data from causing incorrect model training or evaluation. The dataset is split into training and testing sets using Scikit-Learn's train test split function. 30% of the data is kept for testing, so the model can be evaluated on unseen examples. A fixed random state makes the split reproducible, and stratifying by the target keeps the class distribution balanced in both sets. We create a decision tree classifier with a maximum depth of 3 and a fixed random state, so results can be reproduced. The model is trained only on the training features and labels, which keeps the test data unseen for a fair evaluation later. The trained decision tree predicts the classes for the first 5 test examples using their features. The numeric predictions are converted into Iris class names, making the results easier to understand. The actual class names for those same examples are also retrieved, so the predictions can be compared directly with the correct labels. The code measures how accurately the decision tree performs on the test data. It uses the classifier's score method to compare predicted labels with the true labels, and returns the share of correct predictions as a single accuracy value. The output first shows the Scikit-Learn version to support reproducibility. It then compares the model's first few predicted class names with the true class names from the test data, giving a quick visual check of performance. Finally, it reports the test accuracy, rounded to 2 decimal places, summarizing how well the model predicts unseen examples. This script shows a simple machine learning workflow using a decision tree classifier on the Iris dataset. It loads the data, splits it into separate training and test sets, trains the model, and compares predictions for a few test samples with their true class names. It also reports the Scikit-Learn version and the model's overall accuracy on the test set, showing how well it performs on unseen data. Transform methods. Transform methods change data into a more useful form, rather than making predictions. A transformer learns the needed transformation from training data, then applies it to new data. Examples include standardizing features, turning text into numerical features, or reducing data to fewer dimensions for easier modeling, visualization, or analysis. To avoid data leakage, fit a transformer only on the data it should learn from, usually the training data. After that, use transform on training, validation, test, or future data, so the same learned settings are applied consistently. The fit transform method is a shortcut for the initial training data, while transform alone should be used afterward to keep the transformation rules fixed. Transform methods are important in machine learning because they prepare raw data before modeling. They handle issues such as missing values, inconsistent scales, and converting records into useful features. By making transformation a structured workflow step, the same learned settings are applied consistently, while keeping data preparation separate from prediction. Python code. Transform methods. Use transformation methods by learning settings only from the training data, then applying those same settings to new rows. Compare fitting and transforming the training data with transforming new data, and inspect both the learned settings and the resulting feature values. We import NumPy for numerical work and Scikit-Learn for machine learning tools. From Scikit-Learn, we use the train test split function to divide data into training and testing sets, and the StandardScaler to normalize features by centering them and scaling them to unit variance. This pre-processing helps many machine learning algorithms perform more effectively. We create a small NumPy dataset with two features that use very different scales. Each row represents one data point, with one feature ranging from 50 to 100, and the other from 2 to 7. This makes it easy to show why feature scaling matters when ranges differ. We split the dataset into training and test sets so the model can be evaluated on data it has not seen during fitting. Using Scikit-Learn's train test split function, 2 rows are reserved for testing. A random state of 42 makes the split reproducible each time the code runs. A StandardScaler standardizes features by learning the mean and standard deviation from the training data. Applying the fit and transform method to the training features uses those values to rescale each feature so it has a mean of 0 and a standard deviation of 1. This helps the model treat features fairly, even when their original scales are different. The StandardScaler transform method applies the scaling learned from the training data to the test data. This keeps both datasets scaled with the same means and variances. After transforming the training data, check that it still has the same number of rows as the original. If the row count has changed, raise an error, because the transformation may have damaged the data. This simple validation helps confirm that the transformed data remains intact. The process checks that the transformed test data has the same number of rows as the original test data. If the row count changes, it raises an error, because the transformation should not add or remove rows. This helps confirm that the data transformation preserved the dataset's integrity. This example checks the Scikit-Learn version, then reviews the mean values and standard deviations learned by the scaler from the training data. It compares the first test row before and after scaling to show how the learned transformation changes the values. The key workflow is to fit and transform the training data first, then transform new data using the same learned settings without recalculating them. This script shows how to standardize dataset features with Scikit-Learn's StandardScaler. It splits the data into training and test sets, fits the scaler only on the training data to learn each feature's mean and standard deviation, then applies the same scaling to both training and test data. This makes the training features have a mean of 0 and a standard deviation of 1, while keeping test data properly unseen during fitting. The output confirms the row count is unchanged and displays the learned scaling values and an example test row, before and after transformation. Estimator parameters. Parameters versus attributes. In an estimator interface, parameters and attributes serve different roles. Parameters are settings chosen before fitting, either by the user or by default, and they control how the model learns without being changed by the data. Attributes are created during fitting and represent what the model has learned from the data. This distinction is important for understanding, tuning, and reproducing model behavior. Estimator attributes are values created during fitting, showing what the model learned from the data. They often appear only after training and may include things like class labels, coefficients, or cluster centers. Unlike fixed parameters, these learned attributes change from one dataset to another because they reflect the patterns found in the data. In machine learning, parameters and learned attributes serve different roles. Parameters configure an estimator before training, while learned attributes describe what the model discovered after fitting. Confusing them can lead to skit training, incorrect expectations, or misinterpreted results. Keeping this distinction clear is especially important when building pipelines and tuning hyperparameters. Python code, parameters versus attributes. This example highlights the difference between settings and learned results. Parameters are set before an estimator is fitted, while attributes are created after the estimator learns from data. We import Scikit-Learn tools to load the classic iris dataset and build a classification model. The iris dataset loader provides data for a common classification task, and the logistic regression class creates a linear model for binary or multi-class classification. We load the small iris classification dataset from Scikit-Learn for demonstration. The dataset is separated into input features and target labels, so a machine learning model can learn patterns in the features and use them to predict the correct labels. Before training, the code verifies that the feature data and target labels have the same number of rows. This confirms that every example has a matching label, which is required for supervised learning. If they do not match, the code raises an error to signal the mismatch. We create a logistic regression model in Scikit-Learn with a regularization strength of 0.5, a maximum of 200 solver iterations, and a fixed random state of 42 for reproducibility. Before fitting the model, we use the method that retrieves its current settings so we can inspect the configuration. We first check the Scikit-Learn version to support compatibility and reproducibility. Then we inspect the logistic regression model's regularization setting before training. Finally, we confirm that the model has not yet learned its predictable classes, showing that fitting has not started. The model is trained with the fit method, learning from the input features and target labels. Fitting creates learned attributes, often marked with trailing underscores. After training, the getParameters method can be used again to compare the model settings before and after fitting, though in this case, the parameters do not change. After fitting the model, we verify that the regularization setting remains unchanged, confirming the configuration is consistent. We then check the learned class labels to confirm the model identified the target classes from the data. Finally, the coefficient array shape shows the dimensions of the learned relationships between the features and the classes. After fitting a logistic regression model, changing its regularization parameter to 1.0 updates the model's settings, but does not erase what it has already learned. Printing the parameter confirms the new value, and checking the learned class information shows it is still present. This illustrates that changing parameters after fitting does not remove learned attributes. This example uses Scikit-learn logistic regression on the ARIS dataset to show the difference between parameters and learned attributes. Before training, the model has configurable parameters, such as the regularization strength, but it has not yet learned attributes like the classes it can predict. After fitting the model, it gains learned attributes, including the predicted classes and coefficient shape. Changing the regularization setting afterward updates the model configuration, but does not by itself change the learned attributes. Getting parameters. Getting parameters from an estimator means checking its configuration settings, such as how the model is set up to operate. These settings describe the estimator's design and assumptions, not the results it learns from data. Reviewing them helps confirm the options and constraints that shape the model's intended behavior. For transparent and reproducible analysis, it is not enough to know which estimator was used. You also need to check its parameter settings. Choices such as a decision tree's depth or support vector machine's kernel can strongly affect results. Reviewing these settings helps document the model, compare experiments fairly, and ensure collaborators are working with the correct configuration. When using pipelines or meta-estimators, inspect the parameters to understand both the overall setup and the settings of each internal component. Parameters describe what the estimator is told to do, while learned attributes describe what it found during training. Keeping these separate helps avoid confusing configuration with training results. Python code. Getting parameters. Before fitting an estimator, inspect its settings to understand how it is configured. These parameters are different from the attributes learned during fitting. After fitting, compare the original configuration with the fitted results to see what the estimator has learned. We import Scikit-learn tools needed for a simple classification task: the IRIS dataset loader and the k-neighbors classifier. The dataset provides a classic example for classification, while the classifier applies the k-nearest neighbors algorithm to make predictions. We load the IRIS dataset from Scikit-learn, a common dataset for classification. Its features and target labels are kept separate, so a machine learning model can learn patterns in the features and use them to predict the correct labels. Before training a model, the code verifies that the feature data and target labels have the same number of rows. This confirms that every feature set has a matching label. If the counts differ, it raises an error to prevent training on misaligned data, which could cause incorrect model behavior. We create a k-nearest neighbors classifier for a classification task. The model uses 3 nearest neighbors to make each prediction, and with uniform weighting, each neighbor has an equal vote. These simple settings provide a beginner-friendly way to configure the model before training it on data. Before fitting the model, we inspect its initial settings by retrieving its parameters and checking the Scikit-learn version for context. The model is configured to use 3 neighbors for predictions, with uniform weighting, so each neighbor contributes equally. The model is trained by using Scikit-learn's fit method with the feature data and target labels. This teaches the k-nearest neighbors classifier from the data, so it can make predictions later. Fitting also creates learned attributes, such as the classes the model can recognize. After fitting the model, we retrieve its parameters to confirm that settings such as the number of neighbors have not changed. We then verify that the model has learned the class information from the data by checking for the class's attribute. The model's number of neighbors is updated to 5 using the setParameters method, which changes configuration settings without altering anything learned from the data. The updated settings are then checked with the getParameters method to confirm the change. The class's attribute does not appear there because it is a learned attribute, not a configurable parameter. This script shows how Scikit-Learn separates a model's settings from what it learns during training. It loads the iris data, creates a k-nearest neighbors classifier, and checks its initial settings before fitting. After training, the settings stay the same, while learned information, such as the available classes, becomes accessible. The script then changes the number of neighbors, showing that configuration parameters can be updated separately from learned attributes. Updating parameters. Updating estimator parameters changes the settings that guide how a model trains or is used, such as a tree's depth or a nearest neighbor model's number of neighbors. A consistent interface makes these settings easy to inspect and adjust during experimentation. For example, reducing a decision tree's depth can help limit overfitting. But changing a parameter updates the model's instructions, not the data it has already learned. In machine learning, parameters are settings you choose before fitting, such as a penalty type or random seed, while learned attributes are values produced from the data, such as coefficients or cluster centers. If you change a parameter after fitting, the model's learned state may no longer match its configuration. In most cases, you should refit the model so its learned attributes are consistent with the updated settings. Updating parameters through the estimator interface is essential for comparing modeling choices fairly, especially when settings are nested inside pipelines or transformers. It keeps workflows reproducible by defining models through clear settings rather than manual changes. In machine learning, parameters guide the model design, fitting learns from the data, and evaluation shows how well those choices work. Python code, updating parameters. This example shows how to safely update an estimator's parameters. Parameters are separate from the learned attributes created during fitting, so after changing them, refitting is needed to refresh the learned state. We import key tools from Scikit-Learn to build and evaluate a simple classification model. The iris dataset loader provides a standard dataset. The train-test-split function separates it into training and testing data. And the decision tree classifier creates a model that predicts classes from input features. We load the built-in iris classification dataset from Scikit-Learn, which includes both feature values and target labels. The features and labels are then separated, so the data is ready for later processing and modeling. Before training, the code verifies that the feature data and target labels have the same number of rows. This confirms that every input has a matching label. If the counts differ, it raises an error to flag the problem and protect the model training process from invalid data. The dataset is split into training and testing sets using Scikit-Learn's train-test-split function, with 30% reserved for testing. Stratification keeps the class distribution consistent across the split, supporting a fair evaluation. A random state of 42 makes the split reproducible each time the code runs. Create a simple decision tree classifier with a maximum depth of 1, and set a fixed random state so the results are reproducible. Then check the Scikit-Learn version to help track compatibility and any version-specific behavior. Before training, we check the decision tree classifier's maximum depth setting using its parameter retrieval method. Then, we fit the model on the training data so it can learn patterns between the input features and labels. This prepares the model to make predictions on new data. After training the decision tree, we can inspect what it learned by checking the tree's depth. We then test the model by scoring how well it predicts the test labels, rounding the result to 3 decimal places for readability. This gives a quick view of the model's accuracy when the maximum depth is set to 1. We change the decision tree's maximum depth to 3 using the parameter setting method. This lets the tree grow deeper and better capture patterns in the data. We then check the current parameters to confirm the new depth was applied. Refit the decision tree on the training data so it uses the updated parameter settings. Then check the tree depth to see the effect of the new maximum depth, and evaluate its test score to judge how well the updated model generalizes. This script shows how changing a decision tree classifier's settings in Scikit-Learn affects its results. It trains a model on the iris dataset with a shallow tree, reports its learned depth and test score, then updates the maximum depth to allow a deeper tree. After refitting, the learned attributes are recalculated, and the new depth and score show how parameter changes can influence model performance. In this lecture, you learn to explain the roles of estimators, predictors, transformers, and meta-estimators, use fit, predict, transform, fit transform, and score appropriately, and inspect and update estimator parameters without confusing them with learned attributes. In the next lecture, Lecture B, we will go over data contracts.
Thank you for your attention. See you all in the next lecture.